hit a badminton birdie upward with a racket from a height of 2 feet with initial velocity of 8 feet per second. The formula for vertical motion of an object is h of t equals negative 16t squared plus v times t plus s, where v is the initial velocity and s is the initial height. First thing we want to do is to be able to write the equation that models the situation, and then we want to determine how high the birdie is at 0.25 seconds. So if I'm talking about writing the equation that models the situation, just like we did in our previous lesson, we're going to look for the two missing pieces for our equation. We want to know the velocity for the vertical motion, and then we also want to know the starting height. Well, our givens in the first sentence tell us that our initial velocity is 8 feet per second. So this has to go in place for v in our equation. We were also told that it's starting at a height of 2 feet from the ground when it was hit. So that would go in place for s. So a good model for this situation would be h of t equals negative 16t squared plus 8t plus 2. Now for the second part, how high is the birdie at 0.25 seconds? Well, this is a time, and in our problem, time is represented by t. So I have two options of what I can do to solve this part of the problem. I can substitute 0.25 in for t into my function and follow my order of operations to evaluate it for that time. So if I did that with my substitution, right, and then I worked it out, so I would square this, multiply it by negative 16, take this times 8, add each of those terms together, I would end up with a height of 3 feet. That's our algebraic approach. Now, if we wanted to do this graphically and we're using Desmos to help us, I could also do this because our input was 0.25. I could have an input of 0.25 graphically and see what I get out for my result. Now, let's take a look at the graph because we'll probably need to use that for some more pieces to this problem. So here's our basic graph of my function, right? And I can see it here. Now, because we're talking about hitting a birdie, some of these things don't make sense to see on my graph. For example, my heights should be positive values in the real world, as well as my times. If I go back here to the wrench, I could adjust it. I don't really need to see to negative 10 for my inputs for time. Just to make sure I'm staying at 0, maybe I want to make it a negative 2. And I can go and make that a little bit shorter, maybe to 6, counting by ones. In terms of that was for my times, I'm sorry. For my heights, the outputs, again, if I'm talking about heights, I shouldn't have negative numbers, but to see what's happening at 0, maybe go negative 2. And again, we can go up to 6, counting by ones. All right, so here's a better model of my function. Okay, so if I wanted to know about the 2.5 seconds, again, that was an input. And so then graphically, I could substitute that in. Sorry, not 2.5 seconds, it's 0.25 seconds. I can do that, use my cursor to see where they meet, and I can see that it's at 3 feet. All right, now we want to know how long it will take for the birdie to hit the ground. Well, if I'm talking about the birdie hitting the ground, they're giving me a clue about the height. The height on the ground is 0. So I have an output. I want to find the input or inputs that would make that true. So if I think about that, my output being 0, and I have my function here, since I don't know how to solve this algebraically, this is something that I want to do graphically. So I'm going to go back to my graph and put in my second equation of y equals 0. And so that's here at this black line, and I want to see when it hits the ground. Well, if you notice, there are 2 places where the output is 0. The question is, are both of them going to fit my scenario? Is one of them going to fit for my scenario, or are neither going to fit for the scenario? So the one here on the left, we can see that it's at negative 0.18301. Again, this is talking about time that doesn't make sense for our scenario, so I'm going to ignore that value. Here on the right, though, at 0.68301, that doesn't make sense. It will take approximately 0.68301 seconds for the birdie to hit the ground. If we want to round to the nearest tenth, we could say about 0.7 seconds to hit the ground, and we would be on target. All right, the next thing we'll look at is when is the birdie at its maximum height? So again, there are a couple approaches that we can take for this. So if I'm talking about the maximum height, again, for us, that should relate to the vertex for our parabola. So I can see where the maximum is here. Since I'm on Desmos, I can take my cursor and select the maximum value. If I was on my graphing calculator, remember your steps, second trace, pick maximum. It'll ask you for the left bound, move your cursor just to the left and press enter. It'll ask for the right bound, move your cursor just to the right, press enter. It'll say, do you want to guess? No, press enter a third time. At the bottom of your screen, it will say maximum x equals y equals. It should match what we have here on Desmos. So if the question is, when will the birdie reach its maximum height? When is time, and time is our input. So that's going to happen at 0.25 seconds. If they want to know what was the maximum height, that would be the output of my function. So again, if they're asking what is the maximum height, we're looking at the output, and we can see the maximum height of the birdie is 3 feet. So graphically, we have this option. We don't have to solve this graphically. We could also do this algebraically. Algebraically, when we were talking about finding the vertex, remember to find the x value, which represents our time. We take the opposite of b divided by 2 times a. And then that will tell us what time that is happening. So b was 8, a was -16. We substitute it in. We'll end up with a quarter, which is our 0.25 seconds. If I wanted to find what is the maximum height of the birdie, well, now I have the time, I just need to find the height. Algebraically, we're taking the time and substituting it in for t into my function and working it out to see when that results. And so again, this is how algebraically we're getting the same answer we did graphically of 3 feet. Here's another scenario. On the moon, an astronaut tosses a baseball from a height of 64 feet with initial velocity of 23.6 feet per second. The formula for vertical motion of an object on the moon is h of t equals -2.67 t squared plus v times t plus s, where v is the initial velocity and s is the initial height. Remember, h of t represents the height of our function and t is the time in seconds. Again, we want to write an equation that models the situation. So again, as we're reading through, we're looking to see what our givens are, and they tell us the initial height is 64 feet, so that's going to go in place of s. And they're telling us the initial velocity is 26.3 feet, so that's going to go in place of v. So our function should be h of t equals -2.67 t squared plus 23.6 t plus 64. Let's take this and put it into our graphing device so we can use it in the future for different key feature questions and also practice setting our window. So here is our function. This is still the window that we had from before, and obviously it's not working for our scenario. So if we go up to the wrench, again, we're thinking about the time in seconds. We definitely want to see what's happening at 0, so pick something a little bit to the left of that, -2, -1. Definitely need to go past 6 seconds, so I don't know, we'll go to 12 seconds. And you can count by ones. You could also count by twos if you like. That's up to you. And then height-wise, we know that the height is starting at 64 feet, so I want a number definitely more than that. So I don't know, we'll just do a little bit less than doubling, but let's do maybe 120. And then we could count by tens. I still kept it at -2 for my lowest, but I just want to make sure I'm seeing past 0 so I can find some key features to help me. All right, so I can see everything I want to see for my parabola. I can see its turning point, the vertex. I can see some x-intercepts. So it's looking like I'm in good shape. So let's go back to our questions. All right, so it says, how long will it take for another astronaut to catch the ball at a height of 6 feet? Okay, so we have to think about, are they giving us a clue about an input or an output for our function? The astronaut is going to catch the ball at a height of 6 feet. So height, remember, that is in output. So I have a new output to work with, which is 6 feet. So I'm going to introduce another function where h of t is equal to 6. If you want to think about y equals to 6, I want to see where they meet on my function. So let's go to our graphing devices and see what happens. So I entered in my function y equals 6, and I can see it here. One intersection point is going to be over here in just past -2 seconds, but again, that doesn't make sense for our situation since the ball, the ball started at a height of 64 at 0 seconds, right? So we're ignoring this part of our graph for our scenario. So I'm looking to see where they meet, and that's here. Again, graphing calculator folks, you're pressing second trace intersect to find that location. It'll ask you for the left bound and the right bound. Just make sure you're taking your cursor a little bit to the left, hitting enter, to the right, hitting enter. It'll ask you to guess. You don't want to do that. Hit enter again. At the bottom, we'll say intersection x equals y equals. So here we can see we've got 10.84245, So we know after 10.84245 seconds, the astronaut will catch the ball 6 feet in the air. So similar to what we did in our previous lesson and the two problems here today, we're looking at how we can solve our applications using things that we know about the key features on our graphs, right? When is it appropriate to look for the vertex to help answer questions about minimums and maximums, for times, intersecting for different outputs to find the inputs, and so on. So if you take a look at your next page, you have a couple of applications to practice doing the same thing. Please remember that as you are doing things graphically, you need to include your evidence by taking screenshots or snips, just like we've been showing you throughout the lessons in class and on the videos to support your results. You are always welcome to do things algebraically. You might find doing some of that a little bit quicker for you. Just make sure you're including all of that on your papers. Final answers will be checkable on class kick, and we'll resume this in the next lesson.